Hi, everyone. Thanks for joining. So today we're going to talk about how we integrated Ray into LinkedIn Stack and some ways that we've applied Ray to LinkedIn's machine learning use cases. So I'm Jonathan. I'm an engineer on the deep learning infrastructure team at LinkedIn. I'll be covering the first half of this talk about LinkedIn's offline machine learning infrastructure and how we run Ray on Hadoop. And then I'll pass it over to my teammate Nitin, who will talk about how we use Ray for hyperparameter tuning. So the agenda for this talk is we'll first go over LinkedIn's offline machine learning infrastructure. Then we'll talk about some platforms that we built on top of Hadoop that we use to run distributed Ray clusters. And then at the end, we'll talk about how we use Ray for hyperparameter tuning. So LinkedIn's vision is to create economic opportunity for every member of the global workforce. To do this, we have a large data lake to draw on, hundreds of millions of members, dozens of millions of companies that we can use to extract insights for our members. So to better connect people with their next opportunity, we have many platforms that we can use to derive insights from, such as people you may know for recommending connections to members, feed recommendations, jobs you may be interested, and other use cases which we can use to recommend relevant content to our members. So this is the high-level offline infrastructure at LinkedIn. At the bottom, you can see that we are mainly a Hadoop shop. So for our storage infrastructure, we use Hadoop's HDFS. And for compute, we use Yarn, which is Hadoop's resource management layer. Above Hadoop, we use many different compute engines such as MapReduce, Pig, and Hive. But for machine learning specifically, we use mostly Apache Spark, which is a well-known general purpose compute engine, which also includes support for machine learning. And we also use Tony, which is an in-house platform that we built at LinkedIn, which we named after TensorFlow on Yarn. This was originally a use case for running TensorFlow jobs on top of Hadoop, but we have since adapted it to non-TensorFlow use cases such as Ray. And then above that, we use Azkaban, which is another in-house platform that we built at LinkedIn. Azkaban is used for workflow management. So users can chain various types of jobs together to form a DAG to run their jobs in a flow. So our main development Hadoop cluster, our largest cluster consists of 7,000 nodes. It contains 1.8 petabytes of compute memory and over 300 petabytes of storage. We have over 4,000 users running on our cluster with over 200K apps running per day. And then for our machine learning use cases, we have built out a separate cluster that contains over 2,000 GPUs for users to run their deep learning training on. So in addition to Hadoop, we also have built out an experimental Kubernetes cluster that many researchers use at LinkedIn to experiment with various open source libraries. All of our data still sits in HDFS. And so to access this data from Kubernetes, we have built another tool called Kong, or Kubernetes on Grid, which is used to securely access data in HDFS from Kubernetes. So next, let's talk about how we run distributed Ray clusters on Yarn. So to do this, we need to first talk about how Yarn works. So at a high level, Yarn manages all of the compute resources in a Hadoop cluster, and it also provides APIs to users for them to request compute resources from the cluster and then run tasks on the cluster in a distributed fashion. So in Yarn terminology, every application will implement what's called an application master, which contains the user's logic in requesting compute resources from the cluster and then launching tasks remotely on the given allocations. So first, the application master will talk to the cluster to request resources, and then the scheduler inside Yarn will find open slots inside the cluster. Once it finds these slots, it will return them to the application master, which the application master can then use to remotely launch tasks within these containers. So next, how do we bridge the gap between running Ray on Yarn? So normally in Ray, you need to run commands on different nodes that you want to run your Ray cluster on, which includes some manual processes such as finding available ports, and then you need to start your Ray entry points via command line. So instead, to do this, we leverage Tony to do all of this orchestration. So Tony is a generic platform that we use for requesting compute resources on behalf of the user from the Yarn cluster, which includes resources such as memory, CPU, or GPU. We have also handled tasks such as port allocation within Tony itself so that the user running their distributed Ray application doesn't have to worry about that. And then Tony will also handle some application lifecycle monitoring, such as fault tolerance and monitoring the status of the job. So next we'll go through an example of how Tony starts a distributed Ray cluster on Yarn. So for example, suppose the user wants to request a one head container, which requires 2 GB and 1 vCore, and 3 worker containers, each with 8 GB and 2 vCores and 1 GPU resource requirements. So first, the Tony application master will send these resource requests to the Yarn cluster. So once Yarn finds the open slots on the cluster with these resource demands, it will launch containers. It will send these allocations to the application master, and then the application master can launch containers on these given allocations. So here we see we got 2 containers, 1 head and 1 worker on the first node. And at the bottom on the second node, we receive 2 allocations for the other 2 worker nodes. So once these containers have started, then within each container, Tony will allocate a port for this particular process. So for example, in the head container at the top, Tony happened to find a port 1234 that was available on this node, and it will reserve this port for this container. So once all of these containers have found their port allocations, they will send this topology information, including the host and the port that the container is running on, back to the application master. So once the application master receives all 4 of these topology information from the 4 containers, it will aggregate that into a single config and then broadcast this information to every container. So after the application master sends this topology information to the container, it will also send the command that each container is supposed to run. So for example, to the head container, it will tell it to run the Ray start command with this head parameters, since within this container, it will be running the head process for the distributed Ray cluster. And for all the other workers, it will start the command line to start these processes as Ray workers. So next we have a quick demo of how we run Ray on top of Yarn. So here we have a simple code example. At the top, we have this function called getHostName. All this function does is it prints the host name of the machine that this process is running on. And then in the middle, we have this main function, which will call the getHostName function remotely 100 times in a single iteration, and then aggregate the results and print them on the command line. And then we do this iteration 10 times. So here we have the Azkaban flow. So at the top, we have some pre-processing. You can do things like set up your libraries, clean up your data, anything that's required before you actually run the Ray job. In the middle is the actual Ray job. So if we open this, we can see parameters such as the number of head instances. We only want one head and 3 workers. And then we also have parameters for what command that we want both the head and the workers to run. So this is the worker command. So now we go back to the workflow. We can click on execute to run this workflow. This will start the Ray job. And then if we open this execution, we can see these are the logs for the distributed Ray cluster. So we can see at the bottom, there is one head that was allocated and 3 workers. And for each of these components, we can see things such as links to the logs for each of these components. So if we open up, for example, the logs for the head, we can see that Tony is doing some of its setup, which includes the port allocations and sending that information back to the application master. And after that is finished, we will actually start the distributed Ray code. And in this example, it's the get hostname implementation. So here we can see the 10 iterations that we saw previously in the code. So you can see in the first iteration, iteration 0, we have 4 entries in this counter. There's 1 entry for each of the worker, each of the head and the 3 workers. And we can see for each of these hosts, the get hostname remote function ran 25 times. And we can see that printed in the logs. And then we can see that this counter, the aggregation, these 100 iterations were aggregated 10 times. So that is how we run Ray on Yarn. Next, I want to pass it over to my teammate Nitin, who will talk about some use cases that we've applied Ray at LinkedIn.
Thank you, Jonathan. Hi, everyone. I'm Nitin Pasumarthy from the performance team at LinkedIn. And today I will walk you through a small use case of how we used RayTune for building our network quality service deep learning model. For the agenda, we'll first talk about a problem called image optimization and how we use network quality service to solve that problem. And then we'll briefly talk, or we'll heavily talk about how NQS, a network quality service, was built using RayTune. And then finally, we'll wrap up with some aspiring ideas on how we can use AI for solving other performance problems. So images play a big role in engagement at LinkedIn. We see them all the time on feed, network, jobs, company, or any pages. So if we are able to optimize the way images are delivered, we'll see a huge boost, or we have seen in the past as well, a huge boost in member engagement. So anything that helps delivering these images faster is awesome. So one way of doing this is reducing the resolution of image such that it is appropriate, like say on the right hand side here, which is 400 pixels. Now that is great. It will reduce the number of bytes that are transferred over the wire. But however, you can see the quality of the image or the essence of the image is lost. So that will indirectly reduce the member engagement because the image essence is gone. Whereas on the left hand side, if you see, we deliver the original 800 pixel quality. This will improve the essence or the real meaning of the image or the detail of the image, but it will be pretty slow for members who have bad network conditions. So we would like to have a balance between the two and cleverly identify if a member is on a good network or a bad network at runtime at that moment, and see which image we should use for their experience. And that's exactly the goal for this model called network quality service. And we call it NQS in short. It is a service which we designed to be able to predict this type of quality information for every member using their current network information. And we would like to make it like a internal service publicly available so that anyone at LinkedIn, any other team at LinkedIn can use it for their own creative optimization ideas. There are many more use cases and several other inspirational stories of how and why we started NQS, and they are listed in that link below. So we wanted to build NQS for all LinkedIn apps, and for that we have some input features we could use to make a prediction of good, bad, and average network quality. Some features of interest could be where the user is coming from. Are they coming from India, US, Brazil, wherever, whichever part of the world? What network conditions, like which ISP they are connected to? Are they connected to AT&T, T-Mobile, or any other ISP provider? Which device are they using? Which browser are they using to browse LinkedIn on? Using these input features, we would like to create a model that can predict good, bad, or average network quality at that moment in time and expose that to teams at LinkedIn for their users. The idea is fantastic, but there is a lot of work involved in achieving this. As you can see on the right hand side, there are things around resource management. We have uh, lots of GPUs which Jonathan talked about, and we would like to use appropriate number of them for this particular task. We need to also bookkeep all the trials or experiments that we have run and the pros and cons from each of those so that we can plan our next set of experiments. All this is pretty cumbersome, but luckily there are tools like TensorBoard, MLflow, and Ray also to help us here. But the other aspect is the tuning of hyperparameters itself, which involve or which directly impact the accuracy of the model. As you can see, I listed some hyperparameters of interest like what learning rate should we use for the model, what optimizer like ADAM, ADA delta, SGD, any, and what neurons should be there in each model or each layer, how many layers should it include. So many such hyperparameters, and there is no single rule of thumb which says, okay, for this problem, these are the ideal set of hyperparameters. The only way currently that is available is to iteratively experiment different values for these hyperparameters and see how well the model accuracy is. But luckily, there is a ray tune which can help us here, and what we used heavily in NQS design as well. But why is tuning the hyperparameter important? These are the three main reasons for us. One is obviously to get better accuracies. We would like to find hyperparameter combinations that would give us the best possible accuracy for that particular data set. And then we would like to identify these hyperparameters that give us best accuracies in least amount of time. We would like to spend more time on the hyperparameters that would give us better results. And lastly, we would like to efficiently use our resources so that maximum time of resource utilization is spent on trials that lead or probably would lead better models. And Raytune is extensively used in achieving all these three things. Today, we will see 4 approaches in tuning 6 hyperparameters. The first approach is obviously without any help and fully manual is the first thing we did. We tuned complex hyperparameters like the model architecture itself or the base network architecture. Should I use a recurrent neural network? Should I use graph neural network, etc.? Or should I use a deep neural network? However, the challenge with this approach is like the guy in that picture. So we choose a configuration, we leave it to run for few hours, see the result, come back, plan the next set of hyperparameters, see the result and come back. it's a very cumbersome and manual process, like as the name suggests. However, we also, there is another problem actually. We only get to use one GPU here unless until the framework itself supports. In order to solve the resource utilization problem, we switched to Raytune, which immediately showed a huge improvement in all in the usage of all the resources that are there on the node. You can see here on the left hand side, the CPUs are fully busy trying to crunch the numbers, trying to get the model input data ready. And on the right hand side, you can see the GPUs also being very busy trying to use that data and get out an amazing model. Ray helped us in automating all this quite easily. Not only that, with a simple run, I just set up some hyperparameters for exploration using an interesting algorithm called Hyperopt, and I was immediately able to see that the learning rate I was using is low, and I can increase it by I think here it is so I can increase it up to 0.7 in some units to have better accuracies. Hyperopt is an interesting algorithm that is provided by Raytune, which uses a binary search type of approach where it tries some hyperparameters, say on this end of the spectrum, and another hyperparameters of this end at the spectrum, like a very high value, and it looks at the results. Say the results are pretty good in this range, it tries to try more and more hyperparameters around the higher end of the spectrum. And like a binary search approach, it tries to walk through and narrow down the search space, which brings us to a very good configuration of best optimal hyperparameters. That is great, but you can see the problem here immediately. As shown here, there are so many trials, let's say the gray one here, that plateaued in the accuracy at around 14 units of time. But still, Hyperopt doesn't know that it doesn't do any better, or it doesn't use any smart way to stop training it further. That is no smart early stopping. In order to solve that problem, I switched to async hyperband, which is another library in Raytune or an algorithm in Raytune. You can see here immediately that I was able to try 150 experiments in just 14 hours when compared to, I think, 15 trials in 6 hours. Pretty awesome, right? Like a lot of speed up. Not only that, I switched from Hyperopt to Bayes-opt, which is an exploration versus exploitation strategy instead of just exploitation strategy. The idea is you try some trials, check the results, try to exploit the results, best results from those, and train them further. And also, in parallel, exploit new areas. Hopefully, that might lead to better hyperparameter configurations that might lead to better accuracies. That is Bayes-opt. With this combination, I was able to train a lot of experiments, and using a view like parallel coordinates, we can see that with low loss and high accuracy, the hyperparameters should be a high learning rate and a low number of ASN or hashing buckets, which is one of the features that I have used. So this graphic is provided by MLflow, and with Ray's open integration or open interface, I was easily able to integrate both these libraries to provide these amazing visualizations for analysis later. But there is a problem with this approach as well. In this three-dimensional visualization, where I show you on the x-axis the learning rate and on the y-axis the accuracy, you see the dots appearing here are the trials or the experiments. Darker the dot, more recent is the trial. Like that is Bayes-opt, tried a trial, looked at the results, and then tried a more recent trial. We would like eventually to have more number of blue dots in upper half of this chart, right? We want more accuracy as the Bayes-opt is working on optimizing these hyperparameters. But as you see, that's not the case here. There are a lot of experiments, even at the end of the session, with lower accuracies. So You might think that fine, we can tune Bayes' hyperparameters to solve this problem. But isn't this like an inception? We are trying to solve hyperparameters of the model. But in order to get better hyperparameters for the model, we have to tune hyperparameters of the Bayes itself. So I chose a different approach to solve this problem, that is using PBT algorithm. PBT or population based training is another algorithm from RayTune, which is based on evolutionary and genetic theory. The idea is it will try a set of trials, try a set of hyperparameters, pick the best of them after some time, and then modify them a little bit, and then train them further. As you can see, every generation, it tries to pick the best, train them further, and then again try to pick the best from that second generation. This way, we can find the best set of hyperparameters in a very short time. With this approach, I started with the best configurations from Bayes and I trained using PBT. And as you can see, most of the trials in PBT are in the upper half of the corner, just like we expected, right? That's what exactly we want. We want more time to be spent on more promising trials. Another way to look at this result is by seeing how packed each of these trials are. As you can see, I'm comparing HyperOpt, BaseOpt, and PBT with x-axis with the time and the y-axis as the accuracy. Hyperopt spent a lot of time on trials which are not successful. Like you can see these pink color lines. Whereas Bayes was able to use this smart early stopping approach and was spending most of its time on more promising results. But you can see PPT spent almost all the time in a very compact manner. You can see these lines are packed, right? Most of the trials are being utilized or being used for very promising configurations. In summary, we tried four approaches, three from RayTune and one manual, and we saw that how PBT, and I observed that PBT gave a very good result in terms of accuracy. So you can see in this chart, PBT's loss is lower than all the other approaches. However, PBT is having another, it is not as fast as Bayes and HP, but it is spending most of its time on promising trials, though it's not able to explore as fast as others. It's not the slowest, to be honest. Then with this, we deployed it into production and we saw some amazing results. We saw huge improvements in activity of our members, number of weekly active users have increased, and also the revenue has slightly increased. With this amazing positive result, we wanted to scale NQS to other use cases at LinkedIn. And we are in the process of doing that. Not only that, we wanted to extend this tuning concept in a more regular and automated manner so that the models are trained frequently on newer data when the data distribution changes heavily. But besides that, we also want to use AI for other interesting performance problems like choosing the right image compression algorithm based on the type of image, and something like predicting what the members might visit next. Let's say they are going to visit jobs page next. Can we predict and prefetch the results or the page so that when they visit, it will be much faster? So we see a lot of interesting areas where AI can be used. So Praveen and Prasanna are my other colleagues whom I worked with extensively in productionizing, designing this model using RayTune extensively. And we would like to thank Richard a lot for guiding us in many aspects and helping us solving many tricky situations in using RayTune. That's all, folks. Thank you.